So Logan, don't sneeze really loudly because you're right next to the microphone.
Yeah. Okay. What we're going to go over today is we are going to take a step further in phase change. So what we've gone over in phase change up to this point is talking about how you have different states of matter and things are held together differently. We even have a graph that represents that, and that's what the first part of this talks about, is the phase change diagram. Now, if you don't recall the phase change diagram, I can draw it for you right here. Look familiar? You're either a solid right here, you're a liquid right here, or you're a gas right here. And then you could have your phase changes on the plateaus. What we have to go over today is calculating the amount of energy required to make those different phase changes occur. And if you look on your sheet, it gives you an equation, Q equals mc delta T. And that's an equation we're going to become familiar with using. First off, lowercase q stands for the amount of energy. The unit of energy is a joule, capital J. And again, this, you're looking at the same sheet, hopefully, that I have up here. M stands for mass. That's simple enough. If we have a lot of something, it's going to take more energy to melt it. If we have a little bit of it, it's going to take less. C. C is what's called the specific heat capacity. Did you, and again, I only had a handful of you last semester, did you, at the end of last semester, do a simple little activity where you touched the desktop and you grabbed the desk leg? Yep. And they felt different. The desk leg felt colder than the desk top. However, since they're all in the same room, it should all be the same temperature. The reason why they feel different is due to this thing called heat capacity. Based upon intermolecular forces, what holds things together? Different substances have different values for things. Some things heat up fast. Some things do not heat up fast. That's what that C value is representing. Lastly, this triangle is delta, if you know your Greek letters. Delta T is the change in temperature, the final temperature minus the initial temperature. So that is one equation that today we're going to become comfortable with. The second equation I have in bold a little bit further down is that Q equals mass times heat of fusion or heat of vaporization. My hope is that we introduced these terms to you last semester so that now I can give numerical values to those. Because the heat of fusion, if I go back to my smart notebook here, heat of fusion is talking about this right here, melting. To vaporize means you're going from a liquid to a gas. Different amounts of energy are needed for those two different processes. As a matter of fact, I probably should have drew my graph where this was a longer plateau than this one because the heat of vaporization is always a larger value than a heat of fusion. I believe this came up on your final exam, as a matter of fact. You could have either answered it numerically by looking at the graph in the x-axis, or you could have talked about the fact that when you go from a liquid to a gas, you break apart all attraction. That takes more energy than going from a solid to a liquid when you simply loosen things up a little bit. Now, 2/3 of the way down on this sheet then, I give you a whole slew of numbers. You will never have to memorize these numbers. They will be given to you. Quite frankly, we typically give students the two equations in bold that I just talked about as well. Our job is going to be able to use those equations and use these constants to then solve for something. And what we're solving for today is this problem on the very bottom of the board. So the question asks, if you're given 10 grams of ice at negative 10 degrees Celsius, calculate the amount of energy needed to raise the temperature to 110 degrees Celsius. Now, this problem is multi-step, and that's why I have it broken down. I am doing that for you today with notes. However, your homework, I'm not going to say part A, part B, part C, how to solve it. So the hope is today that I can go over how to do this type of problem with you right now, and then you can recognize it takes multiple steps to do. Okay? In order to do this problem, I would suggest just doing it on the back side of this sheet that you're working on right now. So what I'd like you to do is flip to the back side. And first, we always suggest drawing out a heating cooling curve. So draw a heating cooling curve right now. If you don't want to label states of matter because you already know what that is, fine. However, it's going to help you for a reference sake. I mean, if you really wanted to give it the X and Y axis, you could. So remember, 0 degrees Celsius is where the melting occurs for water. 100 is where it occurs for the boiling of water. Okay. So, step number 1 is I would label on my graph, where am I starting temperature-wise? Where am I ending temperature-wise? And on the question on the front side, it says you're starting at negative 10 degrees Celsius. And the question at the end says you're ending at 110. If you're unsure of why I marked down here and up here for those temperature points, just a reminder. Melting occurs at 0 degrees Celsius. So that's why I have to be below that right here. Boiling occurs, or vaporization occurs, at 100 degrees Celsius. That's why I'm above there. The reason why we like to show this to students to start off with, and we suggest they do the same, is that this is a multi-step problem. Step 1 is going to be just heating up my solid. In order to get ice to melt, you have to first heat it up to 0 degrees. Step number 2 is I have to put energy in to melt it, to loosen up those intermolecular forces. Step number 3 then is going to be taking my now melted water and heating it up to 100 degrees Celsius. Because once it has 100 degrees Celsius, now it can start to vaporize, which is my step 4. Finally, when I have steam, I can make that steam even hotter. Now, on the front side of your sheet, it labels it as step A, step B, step C. I'm just doing numbers here instead. Okay? Step number 1. You can see it at the top of the smartboard. I need to take my ice that's at negative 10 degrees Celsius and heat it up to 0. Any time that you're on a slope on this graph, you're going to be using the equation Q equals MC delta T. Logan, flip back to the front side, bottom of the page. What is the mass of ice that we're starting with?
10 grams.
10 grams. So my M value is 10 grams. Danielle, flip back to the front side. There's all those numbers on the front side, right? We need to find the C value. But there's 3 C values listed, isn't there? Right now, in step number 1, we have ice. So Danielle, what's the C value for ice?
1 gram Celsius. Oh wait, 2.03.
2.03. Now the unit's a joule per gram degree Celsius. I apologize for omitting my unit here just to save a little space. Finally, we have to solve for the change in temperature, delta T. That is final minus initial. In this first step, we stop at 0 degrees Celsius. So that's our final temperature. Our initial is -10. So Colton, 0 minus -10 is minus -10 would make it positive, yeah, 10. Zach, without a calculator, 10 times 2.03 times 10. Come on, you can do it. 203. Because 10 times 10 is 100, so. So, what we just solved for, and I apologize if I'm taking this slow, but this is brand new, and when I'll done this, I'll tell you the #1 mistake students make, and it costs them a lot of points on any assessment that we give. Step number 1 is how much energy does it take to heat up our solid? But now it's at 0 degrees Celsius. Step number 2 is we're going to melt the ice. I'll do step number 2 right here, but you can do it down below however you choose. I kind of want to keep the graph shown for a little bit here. In step number 2, there is no change in temperature because any heat added is not raising the temperature, it's breaking apart that intermolecular force of attraction, holding it together as a solid. Because there is no change in temperature, we are going to use this equation on our step 2, on our plateau. So, Caden, what's the mass of the ice?
10 grams.
10 grams. And Sawicki, if you look at the front side, there's 2 H values. There's a heat of fusion and a heat of vaporization. We need to use the correct one at the correct time. Now, secondly, I bet I give you those values in different units, like a kilojoule per mole and stuff like that. How about we stick with the joules per gram version? What's the heat of fusion? 334. Now, the reason why I give you on that front side different units, for example, I bet the heat of fusion of ice is 6.01 kilojoules per mole. Typically, they're reported in kilojoules per mole. However, to have you guys not have to do a metric conversion and a mole conversion in this type of problem, I switched it over for you. Taylor, 10 times 334? 3,340. And joules is our unit. Notice that it takes a lot more energy to melt ice rather than just heat it up a little bit. Okay, now, I apologize, I'm going to have to start moving up and down with the smartboard. But we have just gotten to this point right here that I circled in red. We're at 0 degrees Celsius, but now we're a liquid. Step 3 is we need to go from here to here. We can only take one line at a time. So that's going to be our step 3. I'll even do it in a different color so we can kind of see the different rows that I have going here. So step 3 is once again a Q equals MC delta T, because there is a temperature change when you're at a different state of matter. Emma, what's the mass of our water? 10 grams. It's always 10 grams. No matter what the phase change is, it's always 10 grams. Okay, on the front side, it gives you 3 different C values that are specific for each state of matter. We're in liquid water right now, so what's the C value?
4.184 joules.
4.184. Again, that's our joules per gram degree Celsius, but I'll just omit the unit to save a little space. You do not have to memorize those constants. They will be given to you. However, knowing to use this one instead of the 2.03, because now we're as a liquid water, and water as a liquid is better at absorbing heat before its temperature changes than ice is. That's something that we want you to be able to just recognize which one to use and when. All right, Caleb. Delta T, the change in temperature. Again, our initial temperature started here at 0. Our final went to 100. So finals minus initial would be 100. Start at 0, go to 100. Subtract 2, 100. Ferrigno, can you do this math without a calculator here? Again, I'd take this guy times 10, and then I'd take this same guy times 100. Or you could just take this guy times 1,000. 4,184 joules. We are right where I put the arrow for now. Step 4. We have liquid water at 100 degrees Celsius. We need to heat it up. We need to keep on adding heat, but that heat is going to now break the hydrogen bonds that hold it together. So it's going to stay at 100 degrees Celsius, but it's going to turn into a gas. And because there is no phase change, we go back to M times H. Brian, what's the mass of our water?
10.
So always 10 grams. Conservation of mass. Austin, heat value, the H value, but let's make sure it's the correct one because we're on a different plateau now. 2,263 joules per gram. Haley, multiply those two. 22,630 joules. Notice how much more energy is in our step 4 on the right-hand side to go from liquid to gas than is in our step 2 to go from solid to liquid. When you go from a solid to a liquid, you loosen up those connective forces. When you go from a liquid to a gas, you break those forces completely. It takes more energy to break things apart than just to loosen them a little bit. And numerically, we have proof for that. If I slide back up to my graph, we have just gotten to where I put my green arrow. We're now at a gas at 100 degrees Celsius. Our last step is to get that gas to 110. Anytime we are on a slope of the graph, there is a temperature change. Therefore, we have to use Q equals MC delta T. Tyler, what's the mass?
10 grams.
Creighton, again, make sure we're using the correct C value because different states of matter.
1.99 joules.
1.99, good. Joules per gram degree Celsius.
So as it turns out, steam is the worst at absorbing heat. The higher the C value, the better you are at absorbing heat before your temperature changes. Again, why did that metal leg feel cold on your desk versus the desktop? Metals have really low heat capacities. They take the heat away from your hand right away.
Emily, change in temperature. We're at 100. We have to go to 110. Final minus initial. What's our delta T? 10. Max, multiply those together.
199.
199.
What we have just done in a 5-step process is figured out how much energy does each step take. So in step 1, 203 joules was needed to go from negative 10 degrees Celsius to 0. Step number 2, to turn our solid into a liquid. Step number 3, have our liquid get up to 100 degrees Celsius. Step number 4, have our liquid turn into a gas. And step number 5, our gas get at a higher temperature. The original question asks, calculate the amount of energy needed to make all of this happen. So Drew, what should we do then to finish this problem? Because we didn't calculate the total energy. We just calculated 5 parts. We should add them all together. I'm just going to call this Q total. And I'll do the adding for you here. I'm going to keep it to the whole number. All right? 30,556 joules. Now, some people like to use the metric system. They could call it 30.556 kilojoules. There's one last thing I want to bring up, both good and bad, about what we just did here. First off, we did a calculation. Anytime we do a calculation with measured values, what are we supposed to do with our final answer? We have to round it off to the correct number of significant digits, right? Now, in Chem 1, we teach you the rules of multiply and divide. For example, if I put my decimal in there, we get 2 sig digs here and here, which means I should end up with 2 sig digs in my answer there. Second problem, 2 significant digits. So on and so forth. We don't emphasize in Chem 1 the rules of add and subtract. Because when you start adding all these values together, as Drew said we have to do to finish this problem, then you have to keep track of what place do they have in common last. And quite frankly, that's a little bit trickier of a one. Remember when I talked at the beginning of class about classes that you can take? I'm going to let physics cover that rule a little bit more than I will. If you want to report your final answer like this to the whole number, I'd be fine with that. If you were actually to abide by sig digs, it would end up being 31,000 joules or 31 kilojoules. We will try to de-emphasize sig digs on final answers
if it involves adding and subtracting. But if it's just multiplying or dividing, hopefully you guys remember your rule. Same number of digits. Do we have questions on that at all?